Bom dia a todos, bom dia a todos presentes e todos que estão nos assistindo online. Então, meu nome é Rodrigo Nemmen, eu sou professor do Departamento de Astronomia do Instituto de Astronomia, Geofísica e Ciências Atmosféricas da Universidade de São Paulo. E vamos dar início à defesa de doutorado do candidato Ivan Carlos de Almeida. O título da tese de doutorado é Ventos e Feedback de Buracos Negros, da qual eu fui orientador. Essa defesa de doutorado ela será inteiramente online e o candidato terá um máximo de 1 hora para fazer a sua apresentação, sua defesa de doutorado, que será seguida pela arguição dos seguintes membros da banca. E só um segundo que eu vou começar a gravar aqui. Tinha
Recording
esquecido
in
de gravar.
progress.
Ok, good. Então, o título da tese de doutorado é Ventos e Feedback de Buracos Negros, da qual eu fui orientador. Como eu falei, essa defesa do candidato Ivan Carlos de Almeida ela será inteiramente online. E então, depois da defesa, teremos a arguição, onde os membros da banca farão perguntas sobre o trabalho científico para o candidato Ivan. E os membros da banca julgadora são os seguintes, em ordem alfabética: o doutor Ciriaco Goddi, do IAG.USP, o professor Feng Yuan, do Shanghai Astronomical Observatory, professor Alexander Tchekovskoy, da Northwestern University, a professora Thais Stork Bergman, da Universidade Federal do Rio Grande do Sul, e a professora Zulema Abraham, do IAG.USP. Eu gostaria de pedir a todos que desliguem seus microfones durante a apresentação do candidato. And now let's switch to the official language of the defense. So let's begin the PhD thesis defense of the candidate Ivan Carlos de Almeida in the Astronomy Department of IAG University of São Paulo. The title of the PhD thesis is Winds and Feedback from Underfed Supermassive Black Holes, which was done under my supervision. And I'm very proud of the work that Ivan has done over the last 4 years of his PhD, as you will see in his defense. The candidate will have 1 hour for the oral defense, and the defense will be followed by questions from the thesis committee. And I would like to ask everybody to please turn off your microphones during the oral defense. And now I give the floor to the candidate. So please, Ivan, you may share your screen and begin your presentation.
Okay, thank you, Rodrigo. You all, can you hear me?
Yes.
Okay, so let me share the screen. Can you see my presentation?
Okay. Yes, we can.
So,
Yes.
Well, my name is Ivan Almeida. I am the PhD candidate of the day. I did my PhD thesis under the supervision of Professor Rodrigo Nemmen. And before the presentation, I want to thank you all for participating of my committee. I'm very honored that you all accepted the invitation, and I really thank you all for this. I want to thank you also, Richard, who is behind the scenes, helping with everything on the defense, the point of allowing the Zoom link and things like this. And I'm also thanking you, Rodrigo, is my advisor for the working and learning within the last years. So let's start. My thesis is about wind and feedback from underfed supermassive black holes. And, well, the universe is full of black holes. We have a very high number of them around the cosmos, and they are essentially, we can divide this population of black holes into two main populations. Okay, the stellar black holes, which has masses of some tens of solar masses, and they are hanging around the galaxies. And we have also a population of supermassive black holes with masses that goes from a million to billions of solar masses. And these objects, they live in the center of the giant galaxies. And I focused my work with black holes in this type of population. So everything that I'll talk here is about supermassive black holes, okay? And particular, when this type of objects, or black holes actually, start to accrete gas, accrete matter, they become visible. A black hole in a vacuum is something that's near to undetectable, but when they start to accrete gas, they emit a lot of light and we can see it. In particular, when a supermassive black hole starts to accrete, they become what we call active. Okay? This phenomenon is called active galactic nuclei. Most of the galaxies are not presenting this AGN phenomenon right now, but we expect that all black holes, or all supermassive black holes at some point have this accretion episode. Well, when the black hole starts the accretion process, we have the gas falling into it, forming a spiral, and then onto the black hole. And a lot of things happen during this process. When the gas loses angular momentum through the magnetorotational instability, we have a strong emission of light, the gas heats, and a lot of events happen and these events can, for example, create jets and other types of outflows. Okay. In the AGN phenomenon, the core of this process lies into the central supermassive black hole and the gas falling on it. Okay. While these supermassive black holes accrete matter, they also eject a lot of energy away. Okay. One channel of this ejection is light. Light carries away a lot of energy from this type of systems. And also we have process that leads to the production of matter outflows. Okay. These matter outflows comes in mainly two channels, which is first the relativistic jet, which is a very famous outflow from AGN. We have a very collimated and relativistic ejection from the along poles of the black hole. And also we have the production of some non-relativistic and non-collimated outflows that we call winds. Okay, so here in this work, I will focus on the wind production most of the time. Okay, I'm focusing the AGN phenomenon and most of the time the wind production. So when we have a lot of energy being ejected, this energy must go somewhere. The outflows carry away this energy to the environment. And the environment of the supermassive black hole is the host galaxy in the first moment, and sometimes it can be far away to a galaxy cluster. But talking about more galaxy scenario, we expect that the outflows deposit some energy into the galactic medium, and this deposit will, in the last analysis, will heat up the system. Okay, we are injecting energy in the galactic gas, so some things will happen in the galaxy, and the heating up will have some major consequences into the host galaxy life, the host galaxy evolution. Okay. And well, one thing that I want to point out is that supermassive black holes are actually very small. They are super, but they are so small if we compare with the host galaxy. Okay, the supermassive black hole is not, if you consider a supermassive black hole with 10 to 8 solar masses, we are talking about an object with 1 astronomical unity of diameter, and the related accretion disk will be around 10 to 4 astronomical units. So if we translate these values to parsec scale, the black hole is a microparsec object, and the accretion disk is subparsec scale. And compared to the galaxy, it's nothing. Okay, so can something so small have a noticeable effect on the kiloparsec scales? This is an important question that we try to address. And we have a lot of evidence that these two objects are correlated. Okay? They are strongly linked. For example, if we analyze the mass distribution of the black holes, we have a strong correlation with the stellar population of the host galaxy through this M sigma relation. Okay, somehow the mass of the black hole and the stars of the galaxy are connected, and this is very, very interesting. Now talking more about how this black hole, how this AGN can affect the environment, we can observe some bubbles in clusters, very nice bubbles produced by the relativistic jet that you can observe. And these bubbles are indicating this heating process of the heating of the intercluster medium. We can see the effect of the jet. This has some important effects on the cluster life. If we try to explain the galaxies that we see without considering this AGN feedback, for example, in simulations, the galaxies that we produce in the simulations are not the same as the observations. Okay, but if you add the AGN feedback, somehow we add this AGN feedback process, we see that the galaxies that simulated looks more like the real ones. And also we have some links to the AGN activity and the star formation rate. We expect that this AGN have relation to the quenching of the star formation rate in the local universe from the past, right? So there's a lot of evidences that link these two objects, and we call this relation as AGN feedback. Well, we have these two feedback modes, the most famous in literature. First is the quasar mode that's related to the quasar activity. Quasars are very powerful AGNs that are accreting at high rates. I'm not touched in this type of object, my work, but it's important to say that the quasar feedback is very important in the past, and we expect that quasars have quenched the star formation at some point of the cosmic history. And also have this jet mode, which is essentially the effects of the jet in the environment. Okay, this bubble clusters, some heating that the jet can do. And here in this work, we are exploring possibility of feedback from winds, feedback from luminous AGN winds. Okay, we are exploring the idea of these underfed systems that are the agents in the local universe, they also can help in quenching the star formation. Because if we look to the galaxies nowadays, we don't see a lot of high rates of star formation. So we need some mechanisms that keep the star formation low. Once the star formation was shut off in the equator phase, we expected the star formation to come back, but it didn't. So we need some mechanism to maintain the star formation rate low. And we're exploring the idea of winds from low luminosity agents. Okay, I am working with winds and feedback from in low luminosity agents. Low luminosity agents means low accretion rates. Okay, and in particular, we have a class of objects that present large-scale winds, large-scale heating source in a galaxy that probably are keeping the star formation rate low. Here in this paper, it's the first observation of this type of galaxy from Shanghai 2016. It's the Akira galaxy. Akira galaxy presents an dynamic of the gas that's not compatible with stellar activity. And we can see some kind of asymmetrical structure come from the center. So it looks like what we expect from a wind. Okay, and it cannot be explained by stars. So it's an interesting object to study. In the following years, we have a lot of observations of this type of object, not only Akira, mainly with the work of Narata Roy, not sure how to pronounce the name Roy, in the following papers. And so this Akira galaxy will be our model of galaxy to create a model and try to understand the feedback as an effect of a low luminosity agent wind. So our target are these quiescent galaxies that are called red gazers in these papers, the paper from Sean and the paper from Roy. So in the core of these systems, we expect to have a supermassive black hole and a accretion disk that is in this mode here, this radiatively inefficient accretion flow, right? This accretion disk is geometrically thick, optically thin, and extremely hot accretion flow, and also presents extremely low radiative efficiency. So these objects are not very bright, as the name says, right? Low luminosity agents. And the observations, as I said, they support that in the local universe, the agents are in this RAF mode. We can, for example, look to the SED of one of these objects, and we can model in this RAF very well. So my questions, my scientific questions for this work is, first, what are the mechanisms behind this agent feedback? And if agent feedback is efficient enough to suppress star formation and change the appearance of the galaxy. Okay, this is in the context of low luminosity agent wind feedback. So, well, I'm a theorist. I work with theoretical models, some idealizations. So I am trying to create some toy models, and there's models and simplified models to understand the production of these winds, the production and the potential effect of them. Okay, since we want to understand accretion flows and the impact of winds and galaxy, we need to go to the fluid equation. So I'm working with fluid equation and doing some numerical simulations because if we want to study accretion flows, we cannot do all the calculations by hand. It's impossible. So I need to I performed some numerical simulations, and to use to perform these numerical simulations, I need to learn a bit about high performance computing. I need to learn how to use the computers, the GPUs, the clusters. So, and we need a set of some powerful computers. So my work is this process of modeling and testing, and see what we can explain from a theoretical point of view. Well, I tackled this scientific problem in three main fronts, which are the three main chapters of the thesis. The first one is a study in the accretion disk scales, Almeida did numerical simulations of graphs. So understanding the launching process in the core, the small space of the accretion disk. Also, I want to study feedback, so I need to also study in the galactic scales. So we created a model to estimate the impact of these low noise winds over the galaxy. And also I'm doing some SED modeling of this type of objects, because SEDs carry a lot of important physical informations, and these results can constrain the models. So I need to solve these three fronts to understand the problem big picture as possible. Okay, because it's impossible to, for example, simulate all this thing together. We don't have computational power to do all this at the moment. At least I don't. So let's start with the first part. Okay, just a second. In 2020, we published this paper here, within feedback from supermassive black holes, accretion flow rates, hydrodynamical treatment, which is some hydrodynamical simulations of graphs, and we are trying to model that type of galaxy, Akita, the red geyser. So in our simulations, we found that the accreting supermassive black holes can generate some powerful thermal winds that carry away 0.1 to 1% of the accreted rest mass energy, and the simulations predicted some outflows in the order of 10 to 40 ergs per second. For a system like the Akita, which is in agreement with the observations of this galaxy, and the average velocity of the ejected material was around 300 to 3,000 kilometers per second, also in agreement with the observations. So we have here a video. I expect you can see it. In the top panels, we have the density map of the simulations, where you can see the gas evolving and being ejected along the poles. But I think the most interesting part is the bottom panel, where we plotted the wind efficiency as a function of time. The wind efficiency is just a ratio between the wind energy that the wind carried away against the over the accreted rest mass energy. So this is a fraction that we got as 1%, the energy that the wind carried away. Okay. Well, in a more static representation of the same thing, we have here this evolution of the accretion disk and how it changed, and some ejections along the poles of the simulation. This paper was published in 2020, we reported, and we kept doing this work. But now we move to the Almeida simulations. We used this hammer code. Hammer is the state of art. The Almeida numerical code is based on the code called HAR, and is optimized to be run on GPUs. Well, Hammer is massively scalable GPU accelerated GRMDD code to use a grid-based scheme to solve the fluid equations. I think the motivation for choosing Hammer is because Hammer can be run on GPUs, and the code is very powerful, it's very fast. So we can do the simulation and improve resolution, for example. If you compare with the previous code that we used in the paper of 2020, the Pluto, Hammer is much faster, even if it is a GPU code. Of course, I'm comparing different things because Pluto is a CPU code, but for our purpose, Hammer was much faster. Okay, our GRMDD simulations start with initiators with a density profile of the geometrically thick graph Christian disk. This disk is magnetized. The magnetization is represented first moment by this parameter beta here, which is the ratio between the gas pressure and the magnetic pressure that we assumed as 20 or 100. And we tested some magnet topologies because we want to see the impact of this in the wind production. Okay, and the Hammer solves these equations considering a fixed metric, a metric that's a Kerr metric. So the simulations solve fluid equations under the influence of a rotating black hole. Okay, and we have here a simulation. Here we can see the density map of the simulation and the velocity field lines. I want to take a look in that we have here in the middle an input cone where magnetized, which is the jet, and here along the poles we have some gas flowing out, and these outflows here is what they call the winds of our models. So we try to study the energetics of these winds. Here we have the plot of the energy carried away by the wind over the energy created rest mass energy, okay, for two different simulations. And for each color means that I took this measure at a different radius, the wind energy that is just a surface integral. And we can see that for these simulations, we have an efficiency around 2 to 10%. And if you compare with the thermal scenario that we simulated some years ago, we can see that the magnetic fields, GRMDD, the GRMDD simulation presented 1 order of magnitude stronger winds. Okay, so have this increasing power when we consider the magnetic field. Here we are trying to link the wind efficiency with and the accretion rate profile with some characteristics of the simulations. Here in the left panel, we have the wind efficiency in the y-axis, and the x-axis we have the magnetic flux. And we can see that in each sign here means something, and these stars are the simulations that we consider a spin equals to 0.94, and the circles with spin equals to 0. So we found that we have stronger winds on average in simulations with spin. But if you look to this parameter here, S, which is the slope of the accretion rate profile as a function of the radius, okay, we also, on average, we can have steeper profiles for spined black hole, but have this simulation here that breaks the pattern. But here in this plot, we're trying to show we're trying to understand if there is some link with spin and wind production. I have some hint that yes, but this is result that's it's in literature yet from Sadowski in 2013, I think. And well, this work is not finished. We want to develop better the analysis and publishing maybe in the future. But if the results of the simulations is that the winds reach velocities of up to 0.1, the 0.01 of the light speed, which is consistent with the key observations. The wind power corresponds to 2 to 10% of the accreted risk mass energy. The properties of our simulated winds largely agree with constraint for the prototypical example of luminosity and wind, like the galaxy. We have just slightly more energetic winds, but still very close to the Akita measurements. We found spin has an impact in the wind efficiency, and some occasional bursts got some wind efficiency goes up to greater than 10%. Now let's go to the galactic scale theoretical modeling. Okay, here in this part of the work, I'm talking about analytical model. The simulations are in another chapter. So here we are created a toy model to estimate the impact of low luminosity and winds in a very simplified and generic galaxy. Our galaxy is just a giant spheroid of matter, and all the gas is hydrogenium. And this gas can be described by a velocity dispersion. And we added the low luminosity as a point heating source, the center of the system. And actually for calculations, we assume that everything is spherical. The system has an initial temperature. This is 0. And we expect that the AGN effect over time will slightly increase the temperature of the gas, okay? Because we added a point of a source, a heating source. Okay, so we expect that as the time passes, after a long time, the temperature slightly increase. And gas temperature is a very, very important parameter for stellar formation. So we expect that this injection of energy has some impact over the star formation. Okay. So inside this giant spheroid, we have some clouds. It is the giant cloud of cold gas. And inside of these clouds, we have the protostellar cores. Okay, protostellar cores is the region where stars are born inside the giant clouds. So to form these stars, we assume that the mass of the protostellar core should be greater than the thermogeneous mass. This is a very simplified assumption, but and if the AGN effect over time increase temperature, we assume that this temperature increase is proportional. And we want to understand if this temperature increase due to the AGN activity can affect the star formation. Okay. Here we have a simplified plot of the number of protostellar cores, a distribution with mass. Okay, and the protostellar cores that would collapse into stars would be the ones with masses higher than the Jeans mass. If the protostellar core has a mass greater than this, the gravity will win against the gas pressure and the core will collapse and form a star. If we increase the temperature of the system, the Jeans mass is affected because it strongly depends on temperature. So with the AGN activity, we shift this Jeans mass to a higher value, and the number of protostellar cores that would collapse is smaller. Okay, so we have a difference between these two numbers, which is the suppressed cores, and we defined the quenching fraction as the ratio between the number of suppressed cores due to the AGN activity over the collapsed cores without AGN. Oops. Sorry. This white region, this white number, if you do the integral, is the number, the denominator here. Okay. If Q is equal to 1, we have 100% of suppression, total quenching of star formation. This is what this fraction means. And well, we can link this temperature increase with the low noise AGN properties. If we remember the results from simulations, that the winds carry away a fraction of the accreted energy, so we can estimate the impact of these winds over time. And we have this quenching fraction as a function of the black hole mass, black hole accretion rate, and the time of activity. Okay, for a very long time, higher than 1 mega year, we can start to see this quenching happening, especially for the massive black holes. If in the papers about the Takeda galaxy, they estimated that the wind being active for some mega years. So it's in this time scale here. And the main result of this modeling is that the star formation quenching by the low luminous AGN feedback is a function of the supermassive black hole mass, as accretion rate and the duration of the accretion. For an accretion episode lasting a mega year, a supermassive black hole with mass greater than 10 to 8 solar mass needs an accretion rate of 10 to -3 of the Evanston ratio to about more than 10% of the star formation. And if we increase this time of activity, we need smaller accretion rates to have the same impact. And during this process, we also made some calculations that show that this low noise AGN can reach kiloparsec scales, well, the galaxy size essentially. So going to the last part presentation is about the SED modeling. Okay, SEDs carry very important information about low noise AGN physics. Like if we have an SED, a multi-wavelength SED come from radio to X-rays, we can estimate the black hole mass, the accretion rate, the mass density profile, some information about magnetic fields, and much more. Okay, here, and when I talk about SED, I'm talking about this multi-wavelength this that goes from radio to X-rays, to hard X-rays. And I have some experience with this modeling. This paper from 2018 that we published. We modeled the NGC 3115 SED. We are trying to investigate the possibility of this galaxy to be a target of the Event Horizon Telescope, because it's a nearby AGN, and the angular size is big enough to the EAGT resolution, but it's too faint, so we cannot observe it. But that's the result. And during my PhD, I worked with Ranieri Menezes, and he, in this paper, he found some low noise agents that, and just this is a small detour, okay. He found some low noise agents that present gamma ray emission, and then he asked me to model the multi-wavelength emission of two of these sources, because he was studying the mechanisms of the gamma ray emission, try to understand the phenomenon. And I collaborate with Ranieri, modeling these SEDs of these two objects, NGC 315 and NGC 4261. And this work was published in 2020. And this work creates the seed of a next project, which essentially because here in this plots, in these SEDs, we used a code that calculates synchrotron, Bremsstrahlung, and inverse Compton components for this RAF emission, and the code took 31 minutes to calculate one SED. If we want to perform more robust statistical analysis, a better fit, we cannot. This fit here was done by eye. I change the parameters, see the best fit by eye, and then that's it. Okay? Because we don't have computational power to spend so much time. If we do a lot of SEDs, we took weeks, months, maybe years. So I start to think about this time, how to improve the performance. The original code that generate this RAF, I produced a large set of SEDs in the free time of my computer, like the night, weekends. And with this large set of low-noise AGN SED, I collaborated with Roberto Duarte, another student of our group, and we developed a neural network that calculates the low-noise AGN SED. Here is the scheme of this neural network architecture. For the RAF, for the jet, we have some free parameters, and the input these free parameters, and the neural network output is an array of the luminosity, the power of the luminosity and the SED. We enter the initial parameters, the free parameters, and the code calculates the SED, which is this number, it is just the size of the array. So if we compare the neural network code against the original code, we have a huge speed up in the calculation, okay? We couple this neural network with a code that fits the data, okay? So we are doing the statistics, okay? Go to the statistics and to the fit. And we create this Agnes code. Agnes, you can just give the data points, we need to have some data points. And the code can calculate the better SCD fits. It is the idea of the code. And for the first time, we can do this statistical analysis of the SCD fitting for low noise agents. This is a comparison between the Agnes and the original code. Okay, in each panel we have 2 lines, one for our code and one for the original one. And they are very, very similar, showing the Agnes learned very well how to calculate the luminosity and SCD. Of course, it's neural network, so it has some limitations. Agnes only works inside a range of parameters that we choose, considering the standard scenarios. Okay, and that's it. It's inside this parameter range. Agnes is very efficient. Okay, I just okay. Okay, Agnes is in very good agreement with the shortcode. This is what that box is. So here we have a plot from the paper from 2022 that we published, showing Agnes. And for the first time, we can do a good estimation of uncertainty of this fit. And we have produced some plot like this corn plot, this distribution of the parameters. So this is something that I was very proud about, this idea we have and what we got for the Agnes. So let me summarize the whole presentation now. Just finishing it. We performed some gyro media simulations, studied the winds of the simulations, and we found the magnetically driven outflows with efficiency of 2 to 8%. This work's not finished. I think that we must polish this work and do some maybe more analysis in some points. This is an open project yet, but we got some results, preliminary results. We have this paper about the toy model of luminous agent winds, which is submitted to monthly notices, and I will ensure that have free after the following weeks after my defense. In this, and the luminous agent wind model is our original model for interaction between winds and the galaxy gas, and we predict some relevant quenching transformation for massive luminous agents with this range of mass and accretion rates. It's important to say that this is kind of original analysis, and we have developed this paper is published. Okay, it's about the SCD part of the thesis. We have developed a deep learning method capable of computing radio to X-rays, a spectra of graphs, and we have also the jet part for synchronous emission. And this method is much faster than previous approaches and allows us to apply more robust statistical techniques for the first time for this type of objects. So thank you very much for your attention. And I think I'm done with the presentation.
Thank you, Ivan. Thank you very much for your presentation. So the candidate has finished his oral presentation, and so now it's time for the interaction with the committee members. So the members of the thesis committee can now begin with the question session. Each committee member will have a maximum of 40 minutes. It's a hard limit to interact with the candidate and ask questions about the work. So regarding the order of questioning, so following the tradition, I would like to invite the committee members by order of decreasing order of physical distance from our department. Okay. So here by far the committee member which is farthest from São Paulo, and in fact I'm pretty sure he is very close to the antipodal point of São Paulo, is a Professor Feng Yuan. So Feng, are you here with us?
Yes.
Feng, so are you ready? I would like to invite you to begin with questions to the candidates.
Yeah. Just want to confirm. I need to ask a question for 40 minutes, 540.
No. Yeah, so you have up to 40 minutes to interact with Ivan. Okay, so if you want, you can ask questions during 40 minutes, but it can be as short as you wish, Feng.
Okay.
It's an upper limit of 40 minutes.
Okay.
And making it clear to all the to all the committee members as well, up to 40 minutes.
Should I stop sharing the slides? Or?
I think it's fine because
Yeah, so you can begin, Feng, please.
Okay. First, I want to say congratulations to Ivan, because within the past 4 years, you did excellent and amazing job. It is really true. Very impressive. To summarize, you have performed both HD and MHD numerical simulation of hot accretion flow. You calculated the spectral energy distribution, and also you considered the feedback, wind feedback on the star formation in the host galaxy. You even using AI to do such kind of things. So this is really amazing. I want to say congratulations.
Thank you.
Great job. Yeah. Now I began to ask you some questions and followed by some comments, which hopefully will be helpful for you to consider to improve your work in the future. When you study the wind, you mentioned you consider the effect of the black hole spin. That is great. I want to ask you, what kind of hot accretion flow are you considering, thin or mad?
Okay, I'm trying. Actually, I have some problems with keeping the magnetic flux in the same state for the whole simulation. The magnetic flux start to decrease in my simulations. I'm not sure why, but this I'm trying to always model in the mad state. I have some sane tentatives, but I would say mad. But the magnetic field values sometimes drop below the sane mad limit, you know, the 20. But most of the time it's a mad simulation.
Okay, so I want to mention this point possibly because we published a work in 2021. So we studied both the wind from both thin and mad and consider black hole spin. So it is a good reference to you. I think you can check it.
Ah, yes, of course. What's the? I need to write down what the reference is.
Okay, it is published in 2021 in APJ. The first author is Yuan. I'm the second author. The first author is my student.
Okay.
Okay. So the title is Wind Property Dependence on Black Hole Spin and Magnification of the Accretion Flow. So I am sure you must have interest.
Is that series of papers with numbers 1, 2, 3, 4?
Yes.
Yes.
Okay. This is this is the fourth paper. Yes.
Yeah, okay. The third paper, I think, is our main inspiration for this work. The first and the third one of this series of papers.
Mm. Mm. And you mentioned that the wind speed you obtain is about 1% the speed of light. So
Yes.
I think the wind speed should be a function of the radius. So I wonder which radius are you measuring the wind speed?
Okay. I'm measuring when I calculate the wind efficiency, I need to take into account some surface. Okay. To calculate the energy flux is just the integral of the energy that cross the surface. And I taking at this surface, it's around 200 m and 100 m. I remember well. And I calculate.
Roughly 200 IG, you said?
Yeah.
Okay.
Yes.
Okay. I think this is also important especially because one of your main motivation of studying wind is for study of engine feedback. So we need to know the properties of the wind, including mass flux and the velocity. But as you know, the size, outer boundary of the EDAF or REF is a function of accretion rate. So different accretion rate, the outer boundaries of the hot accretion flow will be different. So this means the wind produced by the hot accretion flow will have different velocity. You know, so this is important to tell the readers at which radius you are measuring the wind velocity. And when we study engine feedback, we need to use different wind velocity, which correspond to different m dot or truncation radius.
I'm not sure if I understood the question.
Do you understand?
I'm not sure if I understand. Is it a question or a comment?
Oh, the first part is a question. The second part is a comment.
So we're talking about in a future publication, we try to study a profile of the speed of the wind. Would be
profile as a function of what?
Radius.
As radius.
Yes.
Okay, that's great. Okay.
So it would be a great possibility.
Okay. Yeah,
Okay.
in our case, we show a figure to say the mass flux weighted wind velocity as a function of radius. You can do the similar things. Yeah.
Okay, I remember this type of plots in papers.
Next question is about the engine feedback study. So you use an idealized model. You put the low luminosity AGN in the center of the galaxy. So my question is, do you decide the accretion rate of the AGN self-consistently, or you just put it as a parameter, as a fixed number?
It's a fixed number of the. In this case, the AGN accretion rate is a free parameter that I choose to explore in the free parameters. And we're talking about feedback in the accretion flow number. Let me rephrase. Talk about the impact of the wind production over the accretion rate. If I take this into account, is this the question? If my accretion rate changes with time?
It's a better way is to you using a self-consistently determined accretion rate, because when you emit wind, the wind will interact with the ISM gas in the host galaxy and push the gas away.
Yes.
Consequently, the density will decrease, so accretion rate will decrease. So this is a self-regulation.
Okay, yeah. The wind is controlling the accretion rate also.
Yeah, this is why we call them feedback. They interact with each other.
Yes. We did not this, and this is a point that that we are working the review of the paper. But in our model, we consider that the accretion rate is fixed as the time passed, and think we need to think more about this. We and Rodrigo have talked a little bit about this some meetings ago, but yeah, now work, very simplified work, we consider this a fixed parameter, and we do not consider the feedback of the galaxy into the interstellar medium into the accretion rate of the black hole. But it's something that will improve the result for sure.
Yeah. Okay. Now let me ask you the last, but perhaps most difficult question. It is again on the aging feedback. You mainly consider the energetic feedback by the aging wind, namely how the wind will heat the ISM gas, increase its temperature so that affect the star formation rate. So my question is, I think you miss something. You miss another kind of mechanism in addition to energetic feedback. So what is that mechanism, you think?
What mechanism I'm missing in the model?
Yes, in terms of the aging feedback, the wind affect the star formation rate. So far you consider the energetic feedback, namely wind will heat the ISM. But in addition to that, we have an additional mechanism in this process. Okay.
Well, since it's a low noise AGN, I'm not expecting to be the radiative field. So I would expect that the wind will carry away part of the mass of this. We have a core, right? Protostellar core, for example. The wind will hit, not the temperature, and it will carry away part of the mass of this core, I think.
Great.
I try to take this after I finished the model. We have made this comment some months ago, and I try to consider this, but in the analytical calculations, I found a very difficult.
This is better to be achieved by numerical simulation.
Yeah. So I don't.
Yeah, this is called momentum feedback.
Yes.
So you only consider the energetic feedback.
Yes.
This is very important because the wind can push the gas away so that change the density spatial distribution. So in this way, star formation rate will also be significantly changed.
Yeah. So our result in the end is some kind of smaller than the reality, probably, because we're not considering this.
Yeah, then, okay, this question will be followed by my comments. So if you consider this effect in the future by numerical simulation, I guess you need to modify your code a little bit. Currently, you just put by hand some protostellar cores you called, okay? If you want to study the effect of the momentum feedback, you need to replace this core by a real star formation rate calculation. That is not difficult at all. If you have interest, I can tell you how to calculate the star formation rate. This is simply some efficiency density divided by some star formation time scale.
If you could send me by mail some papers.
Sure. Yeah, this way, if you inject the wind at the center of the galaxy, then the wind will interact with the ISM automatically in both momentum and energetic sense. So in this way, the density distribution and the temperature will both change. So you can calculate the effect of on the star formation rate. This is much more realistic.
Oh, very nice, very nice.
Okay, I think I don't want to use all of my 40 minutes. That's all of my questions. I already asked this many questions. Thank you.
Thank you.
Thank you very much for the questions, Feng. And as you know, the work by your group has been an ongoing inspiration to our work. So your comments and questions are much appreciated. Very well. So now let's move on to the next committee member. So now we would like to invite Professor Tchekovskoy to ask questions and interact with the candidate. So Sasha, please.
Hey, thanks, Rodrigo. Thanks, Feng, for setting the stage and setting the bar for the questions. And thanks, Ivan, for the wonderful presentation. Great work. So I wanted to kind of start from the basics, and I saw that in many of your plots, you were when you were presenting the results of your really nice simulations, you were showing mass accretion rate m dot measured at 2 gravitational radii. So I was wondering why 2, and would it be different if you measured it at a different distance?
Sure. I have the value of 6 in my mind, but maybe I'm wrong.
Maybe I misremember 2, but that's what I thought. But if it were 6, it's also fine. I'm just curious. You pick a distance and measure mass accretion rate there. You know, you would think naively you would not measure it at the event horizon of the black hole. So why a specific distance that's not at the event horizon? Just curious.
Well, I'm assuming a different radius on the event horizon because, well, I think it's a bit more safe to assume it's not in the scalarity. Well, it's not a problem depending on the coordinates, but this is, well, the usual in the literature that we assume it's placed to the event horizon because probably have maybe some numerical problems there. But I assumed this value based on my reading the literature, but I think it was 6m. Let me check.
I'm looking at your equation 226, for instance, where you say m dot net at 2m. Also,
2m.
Yeah. So I'm just curious. I mean, 2m. I mean, I don't have anything against it. I'm just trying to get you thinking. You know, you can measure that 2m or 6m. Will you have completely different answers, or do you expect similar answers? Do you expect this net mass accretion rate to depend on radius, at least in time average sense? What is the expectation for how net mass accretion rate depend on radius in a steady state in the simulation?
In the steady state, we don't expect that too much difference in the scales, but that it's too close to the black hole, so I'm always a bit of, maybe it's something that since I was using the previous work, Pluto, we cannot be so close because the boundary is not a real black hole, but I don't expect much of difference if I remember the profile, but I think it would be a bit more safe to use it 6m because it's a literature convention, I think. Not convention, but it's usual, right? It's something.
So let me kind of ask the follow-up question. So when you run a simulation, you run it longer and longer, and then a larger and larger region of the accretion flow reaches steady state. So, you know, given how long you have run these simulations, what is the largest distance out to which you think your simulation has reached this sort of quasi-steady state, or sometimes we call it inflow equilibrium?
It's where if I look to the mass accretion rate, okay, have the net, we have the outflow and the inflow, right? And we expect to have some break if we the log plot rate induction rate, I would say it's around this place of the accretion rate.
So what is it like? You ran the simulation out to maybe 50,000 or light crossing times of the black hole. So how far from the black hole does this break in mass accretion rate?
It depends on solution. Okay,
but roughly,
is
it 10 RG, 10 gravitational radii, 100 gravitational radii, 1,000, a million, just to give us an idea?
No, it's between 10 to 100, I think. Let me see if I have a plot here in my presentation. I did not get plot, but it's around 30 to 50.
Oh, that makes sense. And so when you measure the properties of the jets, I see that in your thesis, you have plots of jet power and wind power versus radius that extend out to 1,000 gravitational radii. That seems to be outside of the inflow equilibrium region. So how do you interpret these sort of measurements outside of where it seems like the system is in equilibrium? How do you kind of reconcile these two? Equilibrium is in the small region, and you perform measurements that are very, very much further away.
Oh, okay. Let me think just a bit. We have remember the criterion of equilibrium from Narayan 2012 that we are using the previous work, and if I do have, I forget the formula of the criteria, but if I try to plot in different places, create a map of this population, we have a weird, in the jet is far values, and then the accretion equator have smaller. So why I use it in a place beyond the rotation, the radio of equilibrium? I remember this, if I plot this map, we have higher distance and depending on the angle, but I am considering also that how to explain this.
I mean, like you're saying, does inflow equilibrium depend in some sense, like are all regions in the simulation, like the disk, the wind, and the jets, do they all reach equilibrium out to the same distance? Like what determines how far out a certain part of the simulation has kind of equilibrated with itself? Like, why is it 30 or 50 gravitational radii? What sets that? Like if you were to estimate analytically, how far would you expect an accretion disk to be in equilibrium? That's some time scale, right? So it's length scale divided by some time scale. What is that length scale divided by time scale? Or rather, what is the length scale given the time scale of the simulation that you have carried out?
Well, I could, if I have a viscosity scale, I need to calculate this alpha from the simulation, from some model.
Suppose you have alpha, yeah. You have everything you need, like from the simulation. Even how would you like you can measure the equilibrium distance by looking at m dot, but also can you measure it another way? Like if you have accretion disk that moves faster because alpha is higher, or moves in slower than if alpha is lower, which one would reach inflow equilibrium faster? The one that falls in fast or slow?
Probably that will work. The one with fast will reach fast because of velocity time. It's inverse, right? But I remember I remember doing this mainly another work that the definitions of equilibrium is a bit confusing to me. I remember the definition from the m dot, and another definition that I really forgot that we got from Narayan 2012, that they used the time of simulation and I remember T-chunk. I'm sorry, I forgot this.
Well, if something falls in at velocity v, right, from distance r, how long does it take for it to fall to the black hole?
You can use some, maybe the speed, the sound speeds as a parameter, but probably we need some that alpha times the free fall velocity, if it's on one scale, the viscosity that we can take to analyze this. Speed of light is not useful in this case.
Oh, no. I mean, I'm making your life easy. You already have radial velocity. Like you already computed how fast the disk
okay,
falls
just
in.
times the time.
Okay, so right. Yeah, exactly. So very cool. So if your disk wind is flying out at a pretty high speed, then in a simulation time, it will propagate pretty far, right?
Yes.
So maybe much further out than the distance from which the disk has a chance to accrete. So that's how you can get something that's in steady state locally, the outflow. So coming to the outflow, when you define the different parts of your simulation, the jet, the wind, the disk, how do you break it down between these different components and why?
I choose the entropy because it's a energetic, the way to measure of energy, some A, right? The jet is a region with very, very high energy. So we have the break in the entropy, because the jet's much more energetic. And we have if we took this entropy value close to 1 or -1, depending on the sign, we can see the disk, the torus, and there is a region between the jets and the disk which has a value higher than 1, but not that high like the jet. That is this region of non-collimated outflows that we call winds. We're looking to do this, and this division ends up, that's very similar to the division that we did in the paper of 2020, which is just an angular filter. The jet is 15 degrees, and 15 to 45 is the wind. It's very similar if we do this entropy division. So Jeremy used the entropy, the Bernoulli, actually.
So I'm looking at your equation 227 from your thesis.
220
and 227, 2.27 in your thesis.
Okay.
And so, so can you explain what you're doing here? You have E dot, and then you restrict it to the range where minus H, which is the enthalpy, times U upper T, which is kind of almost Lorentz factor. And it's between 1 and 1.02. So I have two questions here. One is, why do you pick 1.02 as the cutoff? And second question, what is the physical meaning of cutoff of, let me even start with something simpler. What is the physical meaning of minus H times U upper T greater than 1?
Is the binding energy. Okay. So
if it's greater than 1, what does it mean?
It means that is not bounded gravitationally, not gravitationally bound.
But I'm confused because U upper T is essentially Lorentz factor, give or take a positive prefactor. So U upper T is greater than 1, H is greater than 1, and minus H times U upper T, therefore, is going to be negative always. So how can you ever have minus H U upper T greater than 1?
I'm sorry. maybe I just mistake the sign here. Okay, but this is I remember reading papers from Municipality called this Bernoulli, related to the Bernoulli, right?
I mean, if it's Bernoulli, right? I mean, here you would have not a Bernoulli parameter. Then it's basically h. If we look far away, it's basically minus h times the Lorentz factor, right? It's not a Bernoulli parameter. So what would you need to correct in order to make it into a Bernoulli parameter?
H is the enthalpy, the Bernoulli, enthalpy is energy density. Okay, I was confused, so.
So if you're looking for Bernoulli parameter, you probably want to have energy, right? In there, like that includes binding energy, gravitationally.
The enthalpy includes not.
Well, enthalpy includes the heat.
The heat. Yes.
Okay. Yeah, no, that's already included, but there is just one change. I see a typo. It's not U upper T. It's something else related to U. Like what is the conserved energy of a particle in a spherically symmetric gravitational field?
It's negative.
Negative what?
GM over R square GMM. The Newtonian.
Well, that's just the force, but the potential energy would be minus GMM over R. But in general relativity, if you have a particle on an orbit around a black hole, you have, conserved angular momentum and conserved energy. What is the expression for conserved energy and angular momentum in terms of for velocity?
In terms of the for velocity, just we're talking about just solving the geodesics.
Yeah, sure. Like, let's say circular orbits. What is the conserved energy and angular momentum on a circular orbit for a curved black hole in the equatorial plane?
Equatorial plane.
I mean, it's not U upper T. That's my point. Like for the energy. Right, and it's not U upper phi for the angular momentum. It's something else. It's the same exact components, but not upper, but lower components, right?
I'm sorry.
So the conserved energy is minus U lower T, not upper T. Right. So in your equation 227, what I was kind of leading you to is that the Bernoulli parameter is minus H times U lower T, covariant, not contravariant component of the velocity.
Okay. The contravariant.
Yeah, and then the minus sign makes sense, right? Because then U lower T actually is negative.
Okay.
All right.
Right, when we will apply the metrics and change.
Yeah, exactly. So now my next question is, why is it 1.02? Why do you cut it off at 1.02? Because it seems a bit arbitrary. Why that?
Yes, it's arbitrary. By inspection, I did this value and I compared with a paper, I'm not sure if it's Sadowski or Municipality, that we have a value like this. But it was, if I choose to 1.01, it's essentially the same. It's just a cutoff to differentiate the jet and the wind. And I think the one is the point here. Most important to separate from the disk. And we compare the jet and the wind, the value of the jet is much higher. So 1.02 is a arbitrary choice of us.
So if I were to ask, what is the maximum possible velocity this wind can achieve? What would it be?
Velocity is around few 3,000 kilometers per second, a bit more, 4 or 5.
So it's pretty small. So, but there certainly could be winds that are much faster than this. Like we observe ultra fast outflows that can go at, 0.1, maybe even 0.3 C in some extreme cases. Would you be able to capture such winds by this criterion in your simulation?
In my simulation, probably cannot create this type of winds because UFOs are, the mechanism is different. It's radiatively driven winds. So here we have weaker winds than the winds than UFOs. And
but I think that by this criterion, you're limiting yourself to velocities which are basically 1.02. It translates into 1 plus, I think if I'm doing calculations in my head, 1 plus v squared over 2. I think that's what u lower t minus u lower t is. And that means that your maximum velocity of the wind will be square root of 0.04. So that would be 0.2. So you are, I guess you're basically by 227, you're limiting your wind speed to 0.2 C. So that's kind of your division line between the jet and the winds. As far as I understand, is it fair? Is that what you think is going on?
The winds probably much lower, 0.2 in our case, expecting 0.01.
Okay. Rodrigo, I saw you unmuted your microphone for a second. Did you want to say something?
Well, this is interesting because you are suggesting that by construction we might be missing precisely the more faster winds by construction, but
maybe, but not too much.
The difficulty here is really what is the wind, how to numerically tell what is a wind versus the jet sheet.
Yeah. No, I noticed this. No, I noticed this. I now understand that this is similar to what Monica is using, but I was trying to get at sort of the understanding and of the choice of what you're doing here. And I guess another thing is if your division between the jet and the wind is, literally an arbitrary parameter, then what's the right answer? So one thing that I would encourage you to check is like change this parameter, like from 1.02 to 1.04, for instance, or higher, and see if it actually makes any difference. Because my suspicion is that the jets are so much more magnetized than the winds that once you cross a certain threshold, you will go into the highly magnetized region, and its magnetization is way higher than the outside. So basically between the jet and the winds, there is a very sharp discontinuity in magnetization, and therefore the maximum Lorentz factor that you can achieve. And so I think that if you get to cut off right in the middle of this discontinuity between the min and the max, I think that the answer should be pretty insensitive to the value that you pick. So maybe the value you picked is already kind of in that discontinuity, maybe not. So you can just play around with this parameter and see, does it make a difference? And then you can report it as an uncertainty in terms of dividing, your outflow into the jet and the wind, just for us to know, is it robust or not, to divide this. I also wanted to ask you.
So this would be a way of quantifying a sort of systematic uncertainty.
Yeah, because like let's say you have a cutoff at 1.02, and I would have a cutoff at, let's say, 2, and Feng would have another cutoff, and then we would be like comparing our results, and we will be finding different answers. And are we finding different answers because the simulations are different, or because we're just measuring different things? So just kind of understanding how robust the definitions are and how the answer depends on the definition could be interesting, I think. Does that make sense, Ivan?
Yes.
So I
using some magnetization parameter.
Yeah. Pretty much, yes. Like this is a cutoff on magnetization. You can think of it this way too, indeed. But I also wanted to, I think that you can get outflows which are as fast as 0.3 C. they would come from inner regions that are more highly magnetized, maybe not in sane case so easily as in MADS. Because in MADS, you have a full range of magnetization up to very, very high ones, very close to the black hole. And also curious, like you report values of wind efficiency of like 1%, maybe up to 8%. What do you feel like theoretically would be the upper limit of wind efficiency in the sort of non-radiative simulations that you've been looking into?
Sometimes you have some bursts that go close to 50%, but it's fast, very fast bursts.
But on average, what is your idea? Why is it of the order of a few percent or 10%? Is there some physical meaning for why it would be not like much less than 1%, or let's say, why is it not 100% or 1,000%? Why is it around 10%?
Why is it around 10%?
If that's even the correct interpretation, I'm just interpreting your results, that it seems like the maximum efficiencies you found were around 8% or so. So let's say 10%, let's round it up. So what makes 10% special? Is that what you would expect? Is it surprising? Is it boring? Just try to some kind of get a sense of what your take on your findings is.
Okay, it depends on simulation. Okay. If you don't consider the magnetic field, it's much lower, depending on these magnetic fields, but not in a very easy way. Okay, it's a complex relation. Here we don't have, I think it's not so clear like the jet, the relation, the couple of efficiency of the wind, because we have, for example, we can have some thermal components in the wind, have accretion flow, things that happen in the accretion flow, right? And, it can be some, I would say, why is 10%?
Would it help if I ask you like even more frightening question? Let's say, where does this energy come from?
Where does energy come from?
Yeah, where does it come from?
Well, this comes from the gravitational energy. We're losing gravitational energy.
Ah, okay. So something falls in deeper gravitational potential and that energy is released. So what's the upper limit to that? Like roughly, like have you seen the sort of estimates of how deep the gravitational potential is and what sort of efficiency it translates to in any other contexts? Like maybe luminous disks?
Yes, we have the efficiency of 0.1, that's 10%, and the quasar, the thin disk.
Yeah.
So we're asking the efficiency of this low luminosity disk, right?
Yeah.
Really
so what you're finding is the same sort of typical radiative efficiency of quasars. Now, like this is now scary for me. Like, and I'm trying to like, should I be scared or frightened? Are we always finding 10%? And is this a cosmic coincidence, or there is some fundamental physical reason for the two to align? You know, because in one case, quasars are radiatively efficient, right? The disks are really geometrically thin and they're producing radiation. In this case, you have a completely different beast. You know, a geometrically thick disk that doesn't produce much radiation at all. It's in fact non-radiative, right? In your simulations, doesn't produce any radiation. And its mechanical outflow efficiency is roughly 10%, which is similar to radiative efficiency of quasar disks. Why is there any relation? Like, why are the two at all even comparable?
I'm not sure. This is.
I mean, you mentioned gravitational potential. Is the gravitational potential the same in these cases? Maybe that's why. Does it make sense?
The processes are completely different, right? We're talking about 10% of radiative efficiency.
Yeah.
But light, but we're not this.
Yeah, but look, but
Disks.
in order, go ahead. Yeah.
They're totally different disks, and the production of radiation comes from some thermal emission that comes from this thin disk that we measure. They're losing, but I never think about this number correlation, at least because we expect value is much more like 1%. Created energy, things like this is from the observation of this type of object.
So let me ask you then, like I'm trying to deconfuse myself. So if a gas falls into the black hole from a disk feeds the black hole, right? So gas marches from one circular orbit to the one that's closer in and closer in. And so every time the gas falls in closer to the black hole, it needs to go from one orbit to the next, right? Therefore, it needs to get rid of angular momentum and energy in order to match the angular momentum and energy of the new orbit.
Yes.
Right? And that has to happen both in luminous disk and
both cases, yes.
And non-radiative disk. So luminous disk gets rid of its energy through radiation. How can non-radiative disk, the one that you simulate, can get rid of its energy?
Essentially, we have some heating, the gas heated, and this energy is transported by the magnetic field through those layers.
Through the winds?
No. Wait.
So the winds don't take away the energy? But I thought they did.
Take away. Okay, this from the okay. The energy, this missing energy, is carried away by the outflows.
So maybe that's why the two are similar.
Yes.
Very, very cool. Okay, awesome. All right. So let's see. I've asked all. I think I've taken it more than enough time. So this was a lot of fun. I have just one. Let me see. Is it one last question? Yeah, one last question.
Sasha, yeah, you have 10 more minutes if you want.
Oh, have I been asking for half an hour? Oh my God. Okay. I've gotten
no,
carried away.
It's okay. It's okay.
One last question, okay? All right, so one of the free parameters in the Agnes code is the amount of mass loading in the jets. How much mass is there in the jet, as far as I understand? Is that correct?
Is the mass, yes. Yeah, the MEJ is the outflow mass rate.
Yeah, so two-part question. One is, how do we know observationally how much mass is there expected to be loaded on top of the jets? And two, how does this mass loading happen in nature? How does the gas get into the jets in the first place? Because there are magnetic field lines that separate the jets from the outside, so I wouldn't expect any gas to be able to get in. So what's going on?
Okay, this mass outflow rates probably comes from observations. We have some analysis of we have the light, okay, so we can estimate from, for example, can estimate the energy of this type of thing, look into the bubble that the jet produces, and can estimate from this type of process, okay, the energy and the mass we can estimate probably. Well,
I mean, the energy you can, right? You can see how much energy was inflated in the bubble, but mass, can we actually measure how much mass the jets expelled? I mean, there is a lot of mass that is already in the ambient medium, and jets are really, really lightly magnetized. So can we really get down to figuring out that little amount of mass that was in the jet in comparison to what you have in the ASM?
In this parameter, we can, it's like the accretion rate that we cannot measure exactly, but we can estimate from this type of fitting.
Okay. So I guess, let me ask you this question. If jets were really, really heavily magnetized, what sort of observational manifestations would that give us? Could these jets, for instance, move at Lorentz factor of like 10 or 30? if they had lots of gas attached to them.
I'm sorry, could you repeat?
If you had lots of mass dumped by some process into the jets, would you ever expect them to become as fast propagating as they are? You know, observationally, we see these jets propagating at Lorentz factors of 10 or maybe even 15 in some extreme cases. If they had lots of mass outflow in them, would that even be possible? Because if the jet is really heavy and moves that fast, it would carry ginormous amounts of energy.
No, it's it cannot be so heavy, right? We have
yeah, so could that limit, observational limits on Lorentz factor actually tell us about how much mass in the jets?
Yeah, we can estimate from the Lorentz factor that we got from the energy.
Okay, so that's cool. Okay, and now I am like, actually, I've always been confused. I don't know the answer to this question, so I'm curious. What theoretically determines, you know, this maximum Lorentz factor in the jets, like, or the amount of mass that the jets receive somehow, and how would they receive this mass? Just curious about your thoughts.
I think how the mass appear in the jet. I remember reading papers about some pre-production, so some particles that are created in the strong magnetic field, and the light essentially creates particles and interacts the direction of high energetic photons. And these particles probably not, if we have these particles inside the jet, they will be ejected at historically very, very high speed because of the.
But those would be photon annihilation, is that right? So you would have like high energetic photons that would collide with each other and would form electron positron pairs. It's very hard to mass. Is that what you're talking about?
Yes, I remember about some people trying to explain the mass in the jet with this type of production.
I mean, this is a really good idea, but it's really hard to just create that many pairs. Like, you need baryons in the jet to really make them heavy. So
yeah.
That's what I was wondering. How do you get the baryons into the jet, like actual like protons or nuclei?
The accretion disk have a lot of gas, and part of this will interact with the magnetic fields. We have,
but see, these magnetic fields, they're kind of in the way, right? The jet is like this,
it's
right?
in the
So
way.
how do you get things like, it just doesn't compute in my head. So how would you do that?
Maybe we have the interaction of this magnetic tower with the external region of the AGN.
And how would that help avoid this sort of magnetic barrier? How can they get through?
Probably how to avoid the magnetic barrier and enter into the jets.
Yeah, that does make sense what I'm asking. So the jet is like this magnetic spiral, right? And there's this magnetic field that's poloidal and toroidal. And so if you try to get into the jet, you're blocked by this vertical field. That's what I mean by the wall of the magnetic field. So how do you get to mix things into the jets, right? This gas from the outside that's in abundance, but we have a hard time. Simulations have a hard time mixing it into the jet. So that's why I was curious if you have thoughts on how to do that.
Must have some direction in this wall that way, and maybe another magnetic fields that open space. Some, I don't know, maybe have
instabilities, you mean?
Yeah.
Okay. Do you have any instabilities off the top of your head that can mix an interface?
I remember names, but okay, we have the King stability, which changes the modulation. I'm not sure if this is one possibility.
This is a good one. Yeah, King instability sounds good. Cool. All right. Thank you so much. I have asked all of my questions. This was lots of fun. I hope for you too, and that wasn't too scary. So thanks so much, Ivan. Great job.
Okay, eventually I think we have another question about Agnes that I did not answer.
Oh, was there another one? Oh no, I think one was observationally, how do you know how mass loaded the jets are? And
Yes.
and theoretically, how does it actually happen? So we talked observationally first, and then now we are talking about how theoretically this mixing would happen. So I think we've discussed everything.
Okay. Thank you very much.
Oh, thank you.
Thank
This was
you,
fun.
thank you, Sasha. Thank you for the thoughtful questions. Very good. So before we proceed, would you like? I certainly need a few 5 minutes break, bathroom break, let's say. So
I hope it's
is it
not too late
okay?
for Feng.
Okay. Okay.
Yeah,
So we come back in 5 minutes then.
5 minutes. Yes, yes, yes.
Okay.
It's almost 10 p.m. in China.
Feng, are you with us?
Yes.
Okay.
I'm sorry, Feng.
But-
I got carried away. I just had a great time talking to Ivan.
You enjoyed scientific discussion. I understand.
Totally.
So Feng, just to give you so again, Feng, thank you very much. Both for thank you very much. I know this is not a very convenient time. So just to give a heads up of what's ahead, so we have three more committee members asking, interacting with the candidates. It's a long process. But we should finish the whole thing within hopefully 2 hours. Okay, so we'll be it will get late for you, Feng, and then we will deliberate. So in the end, we will deliberate on the result of the thesis. So I hope you'll be able to continue with us. And I apologize for
No problem.
the long process.
No problem.
Yeah, thank you. Ivan, Thaisa, are you here?
I'm here. I'm just finishing my water.
Okay, I'm here.
Okay. So let's proceed. So the next committee member is Professor Storky Bergman. So Thaisa, please, you can begin.
Okay. First of all, congratulations for the advisor and the student for the large volume of work. And I think it's a lot of work and it's very interesting work. And now that we are seeing that, you know, we have these red geysers and more, it's necessary to have this maintenance mode feedback. So it's some feedback that you don't see so easily. I use it to observe outflows in safer galaxies, and you see just the outflow velocities, you know, like 300, 400, up to 800 kilometers per second, but, you know, within the inner kiloparsec. But now that I'm working a little bit also with manga galaxies, where you see I have few observation of the whole galaxy, we see that sometimes the AGN is very weak, but we see disturbances very far away into the galaxy. So how to explain this? And this seems to be a very good option that you have, even if you don't have a bright AGN, you have some feedback that can agitate the interstellar medium. So we see this in manga galaxies that, you know, even though the outflow, the obvious outflow seems to be in the inner kiloparsec, there are some kinematic disturbance propagating out into the galaxy, far away, several tens of kiloparsec.
Yeah, in this set of red geysers, I think it's a paper from Roy. That's some works if this manga.
And I think this Roy work, they found also radio jets, right? Very compact radio jets. So
small radio jets to explain the radio emission.
Yeah.
Well, they look to the galaxy, right? To the gas, and they see a blue shift. It's a blue shift and a red shift on the other side, right? I remember they look for some. I'm not sure if this is the question, but they're looking for some iron lines. And then they found also in the article, there's a paper from Ilya, last year, I think. And they found that we have, this disturbance, first the disturbance is very, they call bisymmetrical, right? Because we have two sides, you can see one blue shifted or red shifted. And when we model the velocity, if we looked only for stars, we see that the data points are slightly above, right? So we have a excess of velocity. And and so this is, I think, the observational signature of this population of red geysers, this bisymmetrical, and the excess of velocity that would be explained by some heating source, maybe from the center of the galaxy, which is linked, in my work, we link it to the low noise AGN.
Okay.
I'm not sure if this is the question.
No, I was just commenting that there has some important applications nowadays. Yeah, and but actually, my questions are mostly about your modeling because I don't know too much, you know, about the theory. So I was trying to learn, and so I learned some things, and I have some questions. Okay. And I will begin not so much from the presentation, but from the thesis. Okay.
Okay.
So, yeah. So in page 38, let's see what I found in page 38. You define the efficiency in terms of MC square, m dot c square, but then you define another efficiency in terms of Eddington luminosity. Okay, why you call these two efficiencies, right?
38.
So it's
Ah, okay.
We call efficiency. For me, it makes more sense. The efficiency being the eta, right?
Yes. This eta comes from the PG. One is I talk about the radiative efficiency and this conversion of dot and the ratio between the accretion rate and the Eddington ratio.
Eddington luminosity. So it just call it the same thing, but maybe it should call different names. I don't know. Okay. And for example, in page 39, are the eta correct in the figure 1.5? Do you have the text?
I think the zeta is actually my epsilon. This is the radiative efficiency. Okay.
Yeah, the radiative efficiency, I don't know if there would be, because there is an arrow upwards.
Yeah, I got the confusion.
Yeah, because then the eta is very small in the bottom, then it begins intermediate in the middle, and then up, small again. It doesn't make too much sense.
No, this here is the radiative efficiency. We expected that rifts have very low radiative efficiency. Okay, the photon, the emission, the light that we see is very weak. And then for thin disks, we have higher radiative efficiency because we can see a lot of light. But if you go to super Eddington, the structure of the accretion disk will be inflated with the radiation pressure, and we expect that the radiative efficiency drops.
Oh, okay. Well, yeah. So I was thinking that the way that you put an arrow pointing to increasing radiative efficiency. So there, in the super Eddington, you don't have higher radiative efficiency. You would have lower. So I don't know. Okay. So the arrow would work for the left side, right?
This arrow is actually indicating the accretion rate. Yes. And,
okay.
I got it.
Yeah, I was confused here. I thought it was a mistake, but then, okay. So the arrow would be only meaningful in the left side. Okay. What else? What is the difference between a slim disk and thin accretion disk? Or is the same thing?
I think the slim disk is in the
page 40. So you mentioned a slim disk, and then you also mentioned thin accretion disk. I couldn't get the difference between them, or are the same thing? Are them the same thing?
Just seeing page 40, right?
Yeah, 40. Yeah. Can be thin or slim disks. Maybe you are okay.
Okay, I'm just confirming the slim disk is a solution for the highest accretion rates for the super Eddington. So it's if you go back to the figure, the page 39, the slim disk is the top one, and the thin disk is in the middle, and the bottom is our RIAF's thick accretion disks, because the slim disks are a bit of different. Okay, because
but they are the ones in RIAFs. Is that you're saying? The ones that the slim disks are the ones that are outside the RIAF structure?
No. Slim disk is a model for the super Eddington accretion rate.
Oh, okay. So the disk
are low.
Yeah. The thin disk that applies for the radiative efficient disk are the same that are outside the RIAFs. Is that what you're saying?
Some models, yes. We have some models with this truncation radius. I remember the paper from Nemmen 2014 where he modeled this RIAF in the close to the black hole, and sometimes need external thin disk, right, to explain the optical observation.
Okay. So you are, do you always have the thin disk, or sometimes you don't have, you just have the inflated structure in the middle?
Well, if I remember, well, looking to the SEDs, sometimes we don't need to
have the
thin disk to explain the SED, but probably because this truncation, maybe the truncation radius is too far away and the thin disk is very small, but depending on the object, actually, when we model it, okay. If you have the emission, the optical, I think we need the external thin disk to explain.
Okay. Another question. I was wondering if you have a number for the gas density. I'm curious to know the gas density in this puffed up part, you know, the RIAF structure, and in the thin disk. Are the densities different?
Yes, they are very different. The thin disk is much denser. The RIAF is a very low density environment for the black hole. Okay.
But you don't have a number. You don't have a number.
Usually you use the accretion rate to parameterize this. I have a number somewhere.
Because I know the densities of the broadline region, that's 10 to the 11, 10 to the 12. Is the thin disk similar, or is higher density?
No, it's much lower in the RIAF.
And the RIAF is much lower. So in the thin would be similar to the broadline region, or not? Is the plasma, right?
Because I don't know in my head the value of density for a thin disk, actually.
Okay. Yeah, I think it's something that you should know.
The value of density. I always work with accretion rates and the velocity. I'm not sure if I have. I will put this type of value in the
okay.
These, because it's important.
Okay.
I will not try it.
Okay. Yeah. Okay. And then there is this famous figure of Rodrigo, figure 1.6. Okay. Yeah. I think Rodrigo draw this. And so I understand that, you know, the winds come from the equations, right? But I think maybe Sasha did this question before. Why do the winds appear? What is the physical driver of this wind?
Okay, the winds in my case, they comes from, they are triggered by we have some Lorentz force that is ejecting it, and also have they are very hot, so we have some expansion, but magnetically driven in this case. It does work. And the energy comes from, as Sasha asked, it comes from, we have a rotational binding energy. As the system loses angular momentum, this energy must go somewhere. And the case of thin disk to generate radiation, in my case, it can trigger some outflow production, because I'm not modeling type of radiation here. We believe that's not that relevant because it's optically thin disk. So, and the radiative efficiency is very low. So from the energy balance, we need to produce these outflows.
On page 42, you present an equation for the viscosity. equation 117.
Yes.
I was wondering, because the viscosity, I know it's present in the thin disks, but is also present in the RIAF, in the ion torus.
Okay.
Viscosity is also present there. This is for the thin disk, or is also for the thick disk?
Here in equation 1.17, right?
Yeah, 117, yeah.
The parameterization of the viscosity from the Shakura-Sinyaev, that's very useful. And we apply to the RIAF model that I was describing for the one-dimensional solution, which is the equations that we are solving to calculate that SED, actually, my thesis. This viscosity is, well, it hides a lot of physical process behind this letter, but probably relate to the magnetic fields and the magneto-rotational instability. That is the way that the angular momentum is transferred. Here we need some way to transport the angular momentum, right? And I think in this particular solution, they are considering that the viscosity is responsible for this, but it's just a parameterization. Is a simplified model that was described in that section.
So you use also in the thick disk, in the RIAF.
Yeah, for the RIAF solution, the one-dimensional solution that is from this Yuan in 2014. But this viscosity, it's hiding much more complex. It's like it's related to magnetic field effect.
Okay. And then on page 43, equation 123.
3. Okay.
Let's see.
Okay, here the electron density.
Let's see if it was this. Let's see.
It's here.
No, I think was not this. It was. I think I got mistaken the number of the equation, because there is some equation where you write dot mass of black hole and also dot m r, m as a function of r. So I understand that dot m black hole is the accretion to the black hole.
Yes.
And then dot m of r, it's accretion at a radius r, right?
Is it 118? 118, equation 118 on the top of page 43?
Maybe.
Or in the PDF, it's 45.
Yeah. Okay. Thank you, Sasha. I got confused. Yeah, okay.
Okay, my notation is bad. Okay, this is m dot BAG is the accretion at the radius RS.
At the radius of the
which is a
Schwarzschild radius? Schwarzschild radius?
Yeah, so it is.
Okay.
That's right.
And then this is different in the dot m of r. Depends on the distance, right? Okay.
Yeah, this is while solving these equations, they assume this power law for the accretion rate as a function of radius. So the power law, I think it's from Bagelman. Learned from Bagelman 99. So it's we assume the power law to solve the equation here in this model. We are astronomers, like power laws. It's reasonable.
So it's it's higher at a larger radius than into the black hole. Yeah.
Yes. And this is indicative of outflow production. because the mass should be go.
Okay, so the mass that doesn't go into the black hole
Yes.
flies away in the wind. Okay. Thank you. So let's see what else. Then I was looking at the SCDs, and I was wondering if the Sagittarius A SCD has any magnetic field component, any jet in the Sagittarius A SCD. So this would be.
This, if you remember, is a paper from Yuan, 2003. They modeled the Sagittarius A star SCD with a RAV model, but since we do not observe a jet, if we point our telescopes there, it's not a clear jet. They explained the radio emission with a population of non-thermal electrons. We have the thermal distribution and also a non-thermal electron population. I don't remember the explanation of this, why this non-thermal population, but something that happened there. But I remember that
it says that there's synchrotron emission, but it's no jet.
Yeah, it's a synchrotron emission from the accretion disk. The RAF can produce. If we look to low noise AGN SCDs, we can see that synchrotron peak. Okay, I mean, you can relate to a population of electron, a very hot electrons that will be in the disk.
So they are if I understand correct, synchrotron emission is because they are spiraling around the magnetic field lines, right? Yes. But the magnetic field in the disk, not in the jet, not in a jet.
A lot of times we need a jet to explain because only the RAF cannot explain. We have, but for the case of Sagittarius A star, I remember this paper that they model the radio emission only considering the RAF with a population of thermal electrons plus a non-thermal electron population that follows some power law.
If I may add, Thaisa, this is a long-standing open question whether Sagittarius A star has a jet or not. I was following the literature on this until I'm not following it closely now, but when I was following it closely, so the thing is, for a resolved jet, okay, people have been looking for resolved jet in Sagittarius A star, and the interesting thing is that with X-rays they find evidence of linear features in the galactic center. Then people find with radio, with VLBA, they find also some linear features, and they found some linear features in gamma rays as well. Okay, over the last 20 years. Now the fascinating thing, in my opinion, is that these linear features, they don't coincide. They are perpendicular to each other sometimes. Okay, so I would be very careful interpreting as jets, but so it's an open question, really.
But there is synchrotron emission. There is synchrotron emission.
If I remember, the EAGT collaboration found that the spins on our points, right? Remember, we have a expected
I remember they said that. Yeah.
Orientation on the system. Unexpected because of, I think we expect one of these axes, observed axis, but yeah, Sagittarius A stars it has some mysteries. So close and so hard to observe.
So I have one more question. On page 53, you make a statement, you say that the kinetic mode is the same as the maintenance mode feedback. And I wonder if this is common knowledge. Where did you get this from? Because I see very strong jets from some galaxies and not so strong jets from other galaxies, or even no jets like Sagittarius stars. So, and kinetic mode feedback, I agree that you can have a jet that can push some interstellar medium and provide kinetic mode feedback. I'm not sure if I agree with this statement, or maybe it's the nature of the outflow or the feedback. So I wonder if you could comment on that. Why you say kinetic mode is the same as maintenance mode.
Okay, okay. We're commenting about the kinetic mode, also all the maintenance modes related to faint regen and jet activity. This is statement, right?
Yeah, in page 53, yeah.
I think maybe it's called kinetic modes, just maintenance modes. It's not that, it's not a perfect statement. But I think it's because we have a quasar phase in the past, right? And we expect that this quasar phase has quenched the galaxy, right? Through the quasar winds, very powerful, and the M sigma relation was created at this time. And later, the quasar stopped it, turned it off, and we have not seen any increase. We don't see increase in the star formation rate like it was before, even if the quasar was turned off. So we need some maintenance mode. And I remember that they related this maintenance of the star formation rate low relating to the kinetic feedback, which is generally studied as the jet feedback. And here we are trying to say, oh, look, we have winds also. It can explain this maintenance mode.
Because you said that, you know,
strong statement that can.
Yeah, no, because you said that, you know, in the RIAF, you have, sometimes you even don't have a jet, but you can have a wind. So you have a maintenance mode feedback, I understand. But so I'm not sure if the kinetic mode feedback is always, you know, maintenance mode feedback. Sometimes the kinetic mode feedback is more strong, exactly. I think. Yeah. So it's just
okay,
that, I'm not sure if you can say that is the same thing.
Okay,
okay. So it's a type of kinetic mode feedback, but you have stronger kinetic mode feedback.
Yeah, I'll have the feedback clusters,
say
right?
it like that. And for example, when you have a quasar, you can, you know, calm down, and then sometimes you have an interaction later on in this history of the galaxy, and you can light up the quasar again. You can have a Cipher galaxy, for example. You know, maybe the Cipher galaxies of today were quasars also in the past, right?
Yes.
So the quasars are more active, and then more in the present day universe, you can have re-triggering of the AGN if you have enough gas, right? So
no, I got it.
Yeah. So
no, the exact mode can be this maintenance mode, but can be more.
Yeah. So this is what.
So you need to write.
Okay. Okay.
Okay. Yes, I agree.
Okay. What else? And then on page 57, you state, we believe these systems are sub-Eddington and hence in RIAF mode. So I understand that the RIAF mode, you need to be not only sub-Eddington, but you have to be like 10 to minus 3 or lower sub-Eddington, right? Because most Cipher galaxies
lower
are sub-Eddington, yeah. Most Cipher galaxies,
okay.
and even some quasars, the quasars nearby, they are sub-Eddington. Many quasars are sub-Eddington. So I think that it's not enough that being sub-Eddington, you're going to have the Ryaf mode. You need to have a lower accretion rate. I think you have to be like lower than 10 to minus 3. So it's just, the text of your thesis. So you have some statements that could be more precise, more.
Yeah.
Okay.
Okay, yeah.
Okay.
Anything about the Eddington is to be Eddington.
Yeah.
It's just...
So it's much below, yeah. So I have pointed out some other statements, like in page 59, you write a statement from Kellerman, 1989. So saying that relativistic jets occur only in 10% of AGN. I think this refers more to, how you say, radio loud AGN, right? That the energy in the radio range is higher than the radiation in the optical range, because now we are finding more and more jets, even in radio quiet galaxies. So
okay.
Yeah, so I think that this number, I'm not sure if this number still holds. This is a bit older reference. So
this number is for radio loud population.
Yeah, I have worked a little bit with some nearby quasars, and they are radio quiet, but they have radio emission. So we are finding, if you have enough sensitivity in your telescope, you can find radio emission at lower levels.
Yeah, we can find some.
Yeah, maybe this 10% would be the radio loud, that you have more energy in radio than in optical, for example.
No, okay.
More power in
the nodes number. Okay. Thank you.
So I wonder if there are winds coming from the region where there is general relativity effects, because you say that, when you get to 30 gravitational radius or lower, then you have general relativity effects, right? And I wonder if the winds would be affected by general relativity effects, or they are outside this inner region where, the general relativity effects are important.
We found that in simulations with spin, we have simulations of spin equal to 0.94 and spin equal to 0. So I will reference with spin and no spin. Simulations with spin, the wind is stronger, but I'm not sure if I'm taking part of the jet into account in this number. Okay, the point is the jet that is, I'm calculating part of the jet. The jet is interacting with the material there and somehow anything. The wind power, I think maybe I'm confusing wind and jets in this sometimes.
No, because you mentioned something. I was reading your thesis, and you mentioned something about that the general relativity was important inside some radius, right? Something like that. I was curious about if the winds appear already in this region, or the winds are more outside this region.
I would say that the winds are a bit outside of this.
More outside, right? Yeah. Okay.
But we have a lot of energy in this region. Maybe the jet can interactive,
Okay.
the process of creating the jet.
Yeah. I have a question also that I wrote here. Equation 2.15 on page 65. I wonder why you selected these beta values, like the ratio between the gas pressure and magnetic pressure, 20 or 100. Why these values? So this is something that maybe
we want to keep some magnetic flux into the black hole. And these values are very common in literature, so this is a way to set
something that is being used in this kind of modeling, and you just kept these values. But
we need some magnetic flux into the black hole, and these values can reproduce the MEDS simulations. So I choose this value based on literature, essentially.
okay. Yeah, so you use it some previous modeling that use these numbers. And also I was wondering about this inclination between the disk and the black hole spin. So you also mentioned 0 and 45. Is there a reason, for these two numbers?
It's arbitrary. Well, the black hole the black hole is not aligned. It's not. There's no obligation that the black hole and the angular momentum of the disk, backward spin, the angular momentum of the disk being aligned.
Okay, it's not.
I just explore this possibility.
Mm-hmm.
The code allow it. It's important to say. It's easy to change this in Hammer. And well, it's kind of curiosity. Let's just see. But I think that for this type of systems, not that impactful.
Okay. So yeah, so it's to consider maybe the most. I would expect maybe the inner part would be aligned, and then outside can be a warp or
the
not
jet is aligned in the simulation. Okay, we have some image of the banded jets from the simulations. The figure is 2.3, 2.4.
2.3. Okay. Yeah. About these figures, I also have some questions about these figures. Here, 2.3 and 2.4 page.
Just a note. We have there are 5 more minutes.
Oh, okay.
Yes.
So I need to stop. Okay. So 70. So I'll make only more these questions. 70. Okay. Yeah. I see in figures 2.3, the panel IB20A9. I found very funny that I can see a disk more or less on the horizontal, but in this case there seems to be an outflow to the right. In the disk there is an outflow instead of inflow. It's sometimes the behavior like that, or
what panel?
I mean page 70,
Okay.
the model IB20A9.
Okay.
To the right here, yeah. I was thinking that the accretion disk would be, the reddest parts. And then I figured that to the right there was arrows going outwards. I don't know.
Yeah.
Yeah, so I found very unexpected, but I guess in the others it's going inwards. I don't know. Okay, so maybe.
Well, now the whole part of it.
Okay.
Maybe it's yeah, it's curious.
Okay. Yeah.
I'm not sure if it's just simulation is not that special.
Okay.
Okay, my figure is in black and white, so it's hard to see.
Okay. Yeah, hard to see the arrow. Yeah, I found peculiar because I decided to look closely and I found these arrows going in. And then, you know, in figure 2.3, they are
sometimes you have
better
some
behavior.
effects. In some simulations, depending of the radius of simulation, have some effect of it's outside of the inflow radius. So imagine that we have in some simulations, if I need a part to go down, some part goes up for the conservation bubble.
Yeah.
And this is not the physical part that we're interested.
Okay, so it's not so.
I need to see better this simulation to.
Okay. Yeah.
The affirmation.
Yeah, just looking closely. And final question is, do you see particles getting into the black hole? This is a stupid question. I wonder. Yeah. Because you are modeling the accretion disk, right? Do you see particles disappearing into the black hole, or it's not part of the simulation? Just curious.
The simulation is it's a geometry code, okay? So the inner boundary is inside of the event horizon, and that's fine. The code can do it. And if part of the gas cross this the horizon, and I think with the boundary condition of the inner region is if the gas cross, they will not come back.
Okay, so they fall into some particles fall into the black hole.
Yeah.
Okay. Okay, thank you.
Thank you.
Too many questions, sorry.
Thank you, Thaisa. Thank you. Certainly very your questions really helped, or were really helpful. Thank you.
Yes, very helpful. Thank you very much.
Right. So thank you very much, Thaisa. And next we have now, I would like to invite Professor Zulema Abraham.
Okay, here I am. Thank you for the invitation. Ivan, you did a good job taking several aspects of AGNs, and I'll be brief. But what I think your presentation was much better than reading the thesis. And what I felt reading the thesis is some comments about who else did, what other works simulations are in the literature, and how they compare with your work. Okay.
Okay. We have simulations from since I think the first one that I remember is on 1999, is the Pringle simulation, the hydrodynamical simulation of this hot accretion flow, and the next years we have a lot of simulations. If comparing my work, I would compare first with my previous work with hydrodynamical simulations.
That's something that is missing also, you know. The chapter 2 maybe should be more about what you did in 2020 than just general things, you know, because you are referring to your previous work, but you don't show it. you could have put it in the thesis, you know.
My master's essentially. So
Yes, but
I can add a
not,
section. You would send it. Section.
Just a description of the results, a better description, okay? But what I meant also is outside your work, what was done before?
Okay. We have some papers from, for example, have papers from Yuan. We have a trilogy of papers that comes from Yuan 2012, 2013, 2015, and now have the fourth of the series in 2021, where they did some simulations very close to this one and to my previous work, and they studied, they dissecate the wind production, and my results, my work is very inspired in this work from Yuan, where they try to constrain the wind and do this thing of efficiency. The idea of tracer particles comes from this work. I'm also inspired by a work from Sadowski, 2012 or 13, the years, I don't remember very well the year, but Sadowski also tried to study this wind production, and he's explored a lot of scenarios like Super Eddington and different from me, but he's also very focused on the wind production. We also have work from Moshbrodska. It's more about the jet, but they talk about winds, and recently we can compare some of my simulations to simulations that people used in the EAGT to create the image. It's the same object that we try to model. There's a lot of simulations that they did this did about the topic. My simulations, we can compare the wind power with the other in the literature. We are very close values to work from Sadowski, for example, that we can compare more face to face. There's also works from Narayan in 2012 that they found weaker winds and mine winds, and then can argue about
why it was so. I mean, what's the reason for the differences? What's different in your model than in theirs?
I think in Yuan 2015 they explained as when they took the average over time, they somehow killed the winds, because the winds are not so. The way you take the average process of the system changes the values. So my work is more aligned with this Yuan 2015 the analysis. So you're suggesting that I improve this discussion section?
I think it's fundamental, because if you're presenting your work, you have to say who did something before and how it compares with yours and why, and what's important in your work that was not in theirs. Okay.
Yes. This work is not totally finished. I probably will continue in my postdoc to finish this work. So it's not polished yet.
I know, but I think anyway in the thesis you should put the references to works that were done before and a short discussion of the difference with your work, because if not,
No, yeah, you're totally correct.
Yeah, okay. But that's okay. As I said, I like very much more your presentation than reading your work. And what I saw in your presentation, I like the movie that you showed. And what I'm referring to, because I like jets more than winds, is that I saw that your jet is not fixed, but it moves, okay, from one side to the other. Is that real? And if it is real, can you calculate, is it something that is periodic? Can you say something about that?
In the video, the jet.
Yes. Can you, do you want to put it again? I saw that at the base of the jet, the jet was moving. Since I like moving jets, I'm presenting jets. I noticed that.
This is
that true?
effect of the lines, not the jet truly moving. That simulation.
I don't know.
Let's see again. But
okay.
Can you see the screen?
Yes.
It's this one, right?
Okay.
We have some.
Oh, in some parts the jets is pointing, I think, in different directions. At least the sides of the jets opens.
Well, I think I need to.
You have to slow down. Okay.
Slow down.
Look at the down part of the jet. I think it moves.
License.
Yeah, there.
I think I need to do a more. More.
Oh, look at that.
Detailed inspection. If it's just a visual.
Well, I don't know.
But if
close to the black hole, not very far away.
I will not make any strong statement about this.
I don't know. I think it's something interesting to look at. That's all. Okay.
Sure it's just some effect of the lines appearing.
Well, but that's what's that? That defines the jet.
Yeah. I'm sorry.
So it would be interesting to see if it. That's okay. You don't have to repeat it, but anyway, it's just a comment because it would be interesting to see if it's a real effect or not. It's something that is expected, you know. If you have a jet that is not in the parallel to the spin of the black hole, you expect changes. I don't know.
But this simulation is parallel. This is why
it's what?
It's parallel in the simulation.
That was parallel?
Yes.
Okay. So you can look at the other one to see if
no, in the other one, yes, we can see some jet.
So it's interesting to see if it's periodic, because that's something that would move the jet. And that comes another question about, you said that you cannot have a jet as an outflow or quenching the star formation because it would be in only one direction. But really, if you have a jet that is precessing, that's something that
increase the angle,
can affect that. And, you know, Diego Falseta Gonzalez and myself and others did simulations, and we showed that the jet in Perseus, the bubbles that you see in X-rays, can be inflated by a precessing jet, by simulation. So that's something that you have to take into account also. It's not only the wind that can affect the quenching, but also the jet.
It's both,
Okay.
right?
The only thing that you need the precession, but it seems that jets are precessing really. So I think Sasha did some simulations that show that also, isn't it?
Yeah, I think the paper that they reported, the first work of Hammer is about the jet misaligned spin and the disk, the Liska 2018 simulation, but for a thin disk.
Yeah.
It was, I think it was for actually disk that was quite similar to the one that you considered. But the precession quickly stops because the disk spreads viscously, and when the disk is big, the black hole, it becomes too small to be able to actually reach far enough where the disk is and cause the angular momentum to precess. And that wobbling of the jet, it's probably some sort of interaction between, asymmetries in the disk with the jet, and maybe instabilities within the jet. So the jet does move around, and if it's turned mad, then the magnetic flux erupting from in different directions can cause the jet to appear to bounce as well. Maybe we've seen something like this in M87. I think there was some Russian who actually wrote a paper who said, "Oh, we've seen jet wobble in M87. That's from MAD." So I was very happy, and that Russian wasn't me, completely unrelated.
Okay.
Thank you, Sasha.
Okay. Yes. My last questions is about your fitting of the spectral energy distribution. What did you put as the physics of the system?
I'm sorry, should you repeat?
Yeah, your fitting of the spectral energy distribution. Okay. What physics is in there in the model?
The model considers three main. For the RIAF, we are taking into account synchrotron emission, which is that the radio, Bremsstrahlung, and inverse Compton. So we have synchrotron Bremsstrahlung, and then the code to the Comptonization of the photons. Okay. Inverse Compton spectrum. So these three mechanisms for emission, and we also add a synchrotron jets. The jet in the jet part.
Okay, so my question is the following: you got a very nice fitting with your model, but if you want to change your model, you will have to make all the simulations again, train your system to decide about the parameters. Is it worse that because every time you want to change the physics that you're putting into your model, you will have to train again? Is it worse in time? I mean, because you know so little about. I mean, you're guessing so many things about the system that I don't know if getting a perfect fitting is worth the discussion. That's my point.
Yeah, I think we have
sometimes just making a guess about what's happening is enough,
I think we have this uncertainty that we have cannot be very well plotted, but every fit have a huge not, but we have some uncertainties that come from this. So we look to the line and we need to say it's more or less this, right? But I think the point of this code is that right now, if I want to fit a low noise AGN, even with this very simplified model, I can just put the data and push play.
I know. Yeah.
Then
for that, you did lots of simulations.
For that, I created a large set of SEGs, they are not simulations. We are solving numerically solving equations that I described in the thesis for the one-dimensional model, a lot of simplifications that carry a lot of uncertainties. But the point is, now we have a very fast tool to this.
For that model you have, but if you change the model, you don't. That's my point. And it's nothing wrong about doing that, but I think you don't have to feel that with that you solve the problem, because if you change your physics, you will have to change your training.
Yes, I'm considering these three types of emission and the very simplified Christian model, the RIFE. If I want something more refined, it fails.
But it will take more time. Okay. I think that's all. Congratulations again to Ivan and to Rodrigo, and thank you for the invitation.
For time, Zulema, really appreciate it.
Thank you, Zulema, for the questions. Thank you very much. And now I would like to call Ciriaco.
Hi, guys. First of all, let me join the other members of the committee in congratulating you, Ivan, for the interesting results you got out from your thesis. And let me also thank you for a super nice and clear presentation. I really enjoyed it. So I think besides doing an excellent theoretical work, you also show to be a very good communicator. So thank you for that. So I have a number of questions and comments, which are mostly, for my understanding, since I'm not a theorist, so I'm sure you will find them very easy to answer. So I'll go in order of chapter, okay, because that's how I know them down. So starting with the introductory chapter, I actually noted down the very basic question on the nature of these winds. I'm really sorry to get back to this after Sasha and Thaisa. Please don't hate me. It's just because I would like to understand a little bit better what these winds are and how they are launched. For instance, in stars, we have stellar winds. In protostars, we have these winds. In both cases, they can be magnetocentrifugally launched or driven by radiation pressure. In this case, we expect radiation pressure to be driving these winds, right? Since in a low luminosity AGN, radiation is trapped. So I noted that in section 2.2 of 60, and this is a more a question for chapter 2, it seems that the wind is material ablated from the coronal region of the disk, and also on page 88, it seems that the winds can be launched thermally. You speak about Parker winds. So is this material that is ablated from the disk because of the extreme temperatures of the accretion flow? Is at least one of the factors driving this these winds?
Okay. Can I have you finished the question?
Yeah, I mean this part of it, because then you also have magnetic fields, and so as you also say, there are Lorentz forces that help ejecting this this material. And then the material also can come actually not only from the accretion flow, also from the jet, right? So I guess the question is if these winds are thermally and magnetically driven. What's the main mechanism?
Okay. In this work, it's magnetically driven. Okay, we have in the previous work that I did, it's only hydrodynamic of simulation. We found some powerful thermal winds. Okay, these winds that we found had purely hydrodynamic simulations. They are one order of magnitude weaker than what we found in the GRM-EDD simulations. And in the previous work, we're essentially saying, look, Winds are a very common feature because they can be thermally driven, and because the system is very hot, it is some Parker wind that's essentially, they are triggered by the expansion of the corona. Very hot, so this they have energy to get away from the gravitational potential. But in the dry immediate simulation, when we add the magnetic fields, our winds are one order of magnitude stronger. So the magnetic fields, probably there is some Parker winds, but it's not the main.
I see. Okay.
Talk about some winds driven by magnetic field and the force, the Lorentz force.
Okay, thank you for clarifying that. Okay, let's continue with chapter 2 on page 46. That's the section 1.73. You write the solution presented in equations 120 to 126. So these are from the one-dimensional model by Narayan and E, 94 and 95. You say this model only works, or these equations only work in the middle of the accretion flow, being invalid in the closest region to the black hole, where a significant part of the radiation comes from. So are these equations invalid because they assume a Newtonian gravitational potential, or are there other important simplifications that make them invalid closer to the black hole?
I think the main part of this is because we are using a pseudo-Newtonian potential.
Okay.
We're just changing a little bit the Newtonian potential. Instead of GM over R, have R means threshold radius. Okay, this changes. This makes some. This is a pseudo potential. Sorry, this is a pseudo-Newtonian potential called the Paczynski-Witte potential. It's used in a lot of works, mainly in the past, because it's easier to solve equation with this potential than go to general relativity. It's much easier. I think the point is this model, this 1D model of section 1.7 don't take into account the GR. Cannot say anything about close to the black holes, a region that the model breaks.
Yeah, okay. So it's because it's not GR, and also it's 1D, and you did 3D version of those equations, so you had to solve them numerically, obviously, and that's the reason for that statement. Okay, so I think I understand now.
Yeah, the simplified model is particularly useful for us to have some insights about the physics.
Sure.
And to calculate SCDs, because we cannot make a whole simulation to calculate one SCD. If you think about the time to spend on it.
Okay, getting to the SCDs, I have a question a little bit related to what was discussed by Zulema. I was actually curious to ask about how long it took to prepare those SCD models from the RIAF models, because you have a table, there are 15,000 SCDs, and you quote 1 minute per model, so that will be 250 hours, 10 days of calculations. Is that a fair figure, or was it longer, or was it shorter?
Okay, the
RIAF, yeah, the RIAF model.
This neural network, actually, let me just see the numbers here. The jet is quite fast.
Yeah, the jet was faster.
So I have a lot of SCDs. The neural network calculated even faster, but the point is the RIAF calculation. This is the bottleneck of the process. Actually, I worked with Ranieri de Menezes in a paper, and I have the idea of why we have a Roberto. Okay, I worked with Ranieri in a paper where I modeled some galaxies that we observed in gamma, and then I looked to this and say, well, how can I improve this process, right? Because it's a code that we use from time to time, right? It's not something that we use on once. And in our group, we have a girl, Roberta, which is the AI expert of the group. And then we work together and look, we have this problem and try to solve. I created the set of graph essentially when I was at the time I finished the work and I let the computer turn it on and play and forget.
Okay.
And if a month creating SEDs, I have a large sample, but it was a considerably long time just creating the set. But
okay, you didn't measure that. No, I mean, the question behind the reason behind the question was that I was a bit disappointed, maybe I'm a bit biased here, that you didn't cover the conditions expected for Sage star, because you cut the accretion rate down to 10 to the -5, edit on accretion rate, right? Well, for Sage star, it should be at least 2 orders of magnitude lower, at least on horizon scales. So I was wondering, well, you said it in the summary that you plan to extend the training set, right? To include also a larger parameter range, spatially or including m dot. And I was wondering how long would it take to extend the range of m dot down to 2 orders of magnitude to include Sage star conditions?
First, I have some problems with the code running with such a low accretion rate. The original code, we can, it's for this type of object, the values start to be a bit odd. Okay, we have some problems in mainly in the comptonization. There's the code, I'm gonna say, we have some parameter that we're looking during the code while code's running. If I go to this very low accretion rates, this parameter sometimes get a bit crazy. So we have a lot of error, a lot of bad SEDs to the sample if we go to low. And this is a problem for the neural network in the training. Okay, so if I want to go to lower accretion rates, I need to somehow fix a bit the codes. I don't know exactly what's this problem, but
sorry to interrupt you. Is the problem in creating the fiducial models to train the code, or is it in the machine learning code the problem?
No, it's in the fiducial code, the original one. It has some the number of SEDs that the code calculates wrong increases as I decrease the accretion rate and decrease the mass of the black. So I don't know exactly why, but I have this set is just filtered with this. I need to do some cut. If I use all the SEDs that I produced, the results were good. In particular for this low accretion rate range, so it's a choice. The range, the final range is a choice, but maybe a forced choice. You know, I can expand, but I need to do.
Okay, so you didn't exclude Sage star on purpose. So there was a problem in reliable your code was to get into lower accretion rates. I see. There is a reason. Well, thanks for explaining that then. Okay, I have
the unique case.
Yeah, but it's an important case, right? It's a unique case.
It's probably the most important because it's our black hole, right?
Yeah, I mean, and you know, there are some observations of that object flying around in the literature. So obviously we have a lot of data that can use. Right. So
okay, go on, please.
Yeah. So I had a last curiosity on the ACD models because both the fiducial models and the ones you get from Agnes if you pronounce it that way, over-predict the optical UV observations, and you attribute this to not an issue with the modeling, but to an observational bias, because one expects strong extinction in the optical UV band, right, due to dust absorption. And I think this is reasonable. It might be the case indeed. I was just wondering if this is then a common and well-known problem in all the SCD modeling, constrained by observations.
I'm sorry, we're talking in the SCD fitting that we overpredict.
Yeah, well, in all, in all the models, the UV points and the optical points, they're always down, right? Yeah, so it's because an observational bias you write in the thesis. So if this is true, then it should be true for all the SCD modeling constrained by observations. Cannot be just in your case, right? So is that correct? Is that a known problem?
Usually for this type of object, we look to X-ray and radio, right? We try to fit these two bands. And it's common that we have some problems with the optical because of extinction, and sometimes observation is contaminated with stellar observation, star emission, and that band is kind of problematic.
So it is never included then. It shouldn't be included because of this observational bias.
I would say that we need to carefully see what we are observing, case by case, and look to the angular side of the observation, resolution. We need because of these problems of extinction and the stellar component. It's not, I think, the best wavelength to study this low luminous events. I would study more of look into the X-ray and the radio.
And the radio, yes.
I trust more this part.
Makes sense. Yeah. Now you say that you write in the thesis that if you try to fit both the UV optical points and the X-rays in some of your objects, either you get one or the other. So you prefer to use the X-rays and forget about the optical because of this observational bias. Fine. Okay. Yeah. Thanks for your answer. Now getting to chapter 4. So in your galactic model, you assume that the gas is in the form of atomic hydrogen, and that's reasonable, of course, for the twin model. But star formation occurs in giant molecular clouds, right? As you point out in your section 4.2.3. And these obviously are made of molecular hydrogen, to a smaller extent to CO and molecules, right? Yeah. So I was wondering if this assumption that the gas is in the form of atomic hydrogen affects to any extent your calculations on the energetics at play, or to put it in different terms, do you expect the increase of gas temperature to be the same in diffuse clouds of atomic gas and in the molecular clouds? Because these are the ones you are mostly interested in, right? Because star formation, when you talk about star formation quenching, you talk about, molecular clouds. So can you comment on this?
I assume that we have an overall increase that's proportional to all the gas content in the galaxy. I think it's a very simplified assumption, but we need to start somewhere. When we go to this, I think the metallicity has an important role in the stellar formation. And I think that considering my analysis is about temperature increases, if I increase some parameter like some thermal, as the terminology is, the metals have a different thermal characteristics than hydrogen. Okay, so I expect that this different can play some role. But another thing that Feng has pointed that's about the mechanical effect. So I think there's a lot of room to improve the model. But yeah, we were asking about the metallicity effect, right?
Well, you know, of course, it's not only hydrogen, but also the fact that these are molecules, right? So it's not, these are not atoms. So it must change something in your energetic calculation, I thought, naively.
Yes,
I will think that.
And some part of the calculations, I need to assume the mass of the particles, right? So probably increase. You need that Z to take into account another population of gas or molecules. But you need to, I would say that it's hard to, I'd say that would be.
No, I understand this is a simplified toy model. Actually, you mentioned metallicity and mechanical energy. I had two small comments on that because you do, you make a couple of conclusive statements, which are very interesting. You say galaxies are under the influence of low luminosity AGN feedback will have smaller metallicities. And now this will be definitely a major consequence, but I'm not sure I agree with it, or better. I'm not sure you have strong evidence for this. Why? Because heavy elements are processing massive stars, right?
Yeah.
And it's true that there are several possible theories of formation of massive stars, including quiescence of small cores to form a big one. The most popular is formation through gravitational collapse of a massive warm or hot core, right? So if this is true, then I don't know if the feedback from AGN wind and the modest increase in temperature will have an important impact on the fragmentation and collapse of these massive cores, the ones that are leading to the formation of massive stars. Yes. So this is my impression. So what I wanted to say is that maybe that statement is a bit premature without a more detailed modeling. I don't know if you agree with this.
No, I got saying I agree. I think the model is very simplified. We cannot do really strong statements, but I think it's worked like a hint to further research about the topic, right? It's like, look, we have something here. Let's improve the model. But, we don't.
And an additional statement there is. You write, our model assumes a smooth wind that interacts with molecular clouds, hitting them up over millions of years. In a more realistic setting, outflows likely strip gas clouds. But I guess this wind is very diffuse, right? Giant molecular clouds, and especially the cores that are forming in them, that are the ones you are mostly interested in, because they will be forming stars. They're still tiny objects, right, on galactic scale. So I guess you will need to compare the mechanical energy of the wind on the relevant scales of the cores to understand whether the wind can actually affect the structure of these clouds and the cores in the interstellar medium. Again, you make this point clear that the model is just a simplified model, and that there is no treatment of the interstellar medium complexity. We know that interstellar medium and star formation is a very messy business. So that's all fine. So don't take this as a criticism. I just wanted to, get your impression on this, and maybe a little bit smooth these final sentences once you are, submitting the final version of the thesis, and make this clear. This is a possibility, but without a detailed modeling, we cannot say much about the metallicity or about the disruption of cloud structure because of the AGN wind. That's my 2 cents suggestion for you on this last chapter. Yeah, and that's all I have. Almost 20 minutes. I tried to be fast. Sorry, I know I was the last one. You must be exhausted by now. Again, congratulations. I really enjoy reading your work and seeing your presentation, and you are out of the hook. Okay.
Thank you very much.
Thank you, Ciriaco. Thank you for your feedback. No pun intended. Was really the comments on the yeah. So the toy model really, it's a toy model. So we are looking over many complex and important physics.
If you want to address all this, we need to go to some simulations beyond the analytical work. But thank you, Ciriaco, for your comments. They're very helpful. And thank you all of you for this. I think I need to go.
Yeah, so let me proceed here. So let me thank again all the committee members. So proceeding here with the process. So all members of the thesis committee had the opportunity to ask questions about the work of the candidate. The thesis committee will now convene at a private online room for the final deliberations, and we will meet back in this public room in about 10 to 15 minutes to announce the result of the defense. So let me now create the breakout room.
So can I stay here, right?
Yes, you stay here, and I am. Let's see, how do I? Richard, você tá por aí? Tá ótimo, tá ótimo.
Obrigado, Richard.
Okay, so Richard is creating a breakout room, and we'll put the committee members and the advisor there. So please accept the invitation to join the breakout room. Are we all back here? Yes. Okay, Zulema, are you here as well? Ivan?
I'm here.
Okay. Okay, Zulema is here. Great, great, great.
Yes.
Okay, so the committee members we met and we discussed the work, and we all agreed on the high quality of the work. And I would like to announce that the PhD was approved by unanimity. So Ivan, congratulations.
Thank you.
Congratulations for your PhD thesis. It has been approved.
Congratulations.
Thank you all for
Congratulations, Ivan.
Congratulations.
thank you, thank you.
And
Okay.
so yeah, I would like to especially congratulate you, Ivan, on the high quality of your work, on the many years of dedication, on the span of the work. You know, like you were very prolific and excellent student, and I wish you success in your career and your future endeavors. I'm really proud of your work. And so congratulations, Ivan, again. Thank you to all the committee members again. I thanked many times, but only one more time, because I know our time is precious and we have a lot of stuff on our plates. So thank you again.
Okay.
And that's it. For people watching the thesis defense online, so this is the end of the defense. The PhD was approved. So thank you for watching, and this is the end. Thank you again.
Okay.
Thank you. Bye-bye.
Thank you.
Bye. Thanks,
Thank
everyone.
you.
Bye,
Congrats.
everyone. Ciao,
Bye.
ciao.
Recording stopped.
Okay.
Beleza. Okay, bye-bye.